Welcome to this video on limits and derivatives, the mathematical language of change. As A.N. Whitehead noted, calculus provides the key to applying mathematics to the study of nature. Imagine trying to find the exact velocity of a falling object at one specific moment. Because velocity is distance over time, calculating it at an instant leads us to divide by zero. We need a new approach to measure the journey, not just the destination. Enter the limit. A limit allows us to analyze what happens to a function as the input gets infinitely close to a target value, without actually arriving there. For a limit to exist, the function must approach the same value from both sides. Limits behave predictably across basic arithmetic. Whether you are adding, subtracting, multiplying, or dividing two functions, limits distribute seamlessly across these operations, provided the individual limits exist. When you encounter a 0 over 0 paradox, you can often solve it by factoring and canceling the term causing the conflict. Once that term is removed, you can evaluate the function through substitution. The sandwich theorem is another powerful tool. If a function is trapped between two others that converge to the same value, the middle function is forced to converge to that same point as well. This helps prove fundamental trigonometric limit. The derivative, represented as f prime of x, formalizes the instantaneous rate of change. It uses the limit of the difference quotient, effectively shrinking the horizontal interval to zero, to find the exact slope at a point. Geometrically, this represents the transition from a secant line connecting two points to a tangent line touching only one. As the gap between points shrinks to zero, the slope of the secant becomes the exact slope of the tangent. While addition is straightforward, products and quotients of functions require specific structural rules, known as the Leibniz rules, to differentiate correctly. Using these principles, we build a standard toolkit for derivatives, including rules for constants, powers, polynomials, and trigonometric functions like sine and cosine. In summary, calculus allows us to move from an average rate of change to an instantaneous one by using limits to bypass division by zero. It is a logical construction designed to capture dynamic motion in mathematical terms.